The accelerated development of artificial intelligence and robotics allows humans to augment and to increase our intellectual output. Here I illustrate actual cognitive machine learning engineering prototypes developed in our Design R&D Center located in Medellin's Software Valley Technology Park. There will be challenges impacted by the deployment of artificial intelligence worldwide. Equally as important, humans will also benefit from the application of artificial intelligence. It is obviously a paradox. The Autonomous Artificial Intelligent Robotic Project presented in this video implements mathematical algorithms and statistical models used to perform several tasks. The machine learning algorithm are used to build mathematical models based on sampled data known as training data in order to make predictions. Supervised learning algorithms include classification and regression. Classification algorithms are used when outputs are restricted to a limited set of values, and regression algorithms are used when the outputs have numerical value within a range. The Autonomous Cognitive Artificial Intelligence platform presented in this video consists of a sophisticated design methodology applying effective computing analytics, artificial neural network mathematical models, cognitive reasoning, neural science including synthetic intelligence software models, which is presented in the engineering prototypes and architectural models that I have developed in the design centers in Miami, USA, and Medellin Software Valley. Cognitive computing is a paradigm based on scientific disciplines of artificial intelligence and signal processing such as DSPs. These platforms encompass machine learning, natural language processing, speech recognition, vision, reasoning, and object recognition. In this project, I will illustrate the use and application of cognitive machine learning in artificial intelligence. Here, I will present the new design methodology for the autonomous robotic system. Cognitive-based models of intrinsic motivation. The first computational approach to intrinsic motivation is based on measures of resonances between the situations experienced by the autonomous robotic and the knowledge and expectations that the robot has about the situation. The reference to a passive observation activity in which the autonomous robotic system does nothing but focus its attention on a specific aspect of the environment, as to an active activity in which the robot performs actions and compares the actual outcome of of its actions to its knowledge and cognitive and expectations about these actions. Information, data, and distributed models. The approach is based on the use of representations built by the autonomous robotic engine that estimates the distributions of probabilities of observing certain events is to the k power. Specifically, contexts defined as mathematical configurations in the sensory motor. There are several types of such events, but the probabilities that are measured are typically either the probability of observing a certain state S of m to the k power in the sensory motor flow, denoted by the equation P times Sm to the k power, or the probability of looking at particular transitions between different states. Cognitive predictive models presented in this illustration are based on the use of predictors such as neural networks or the support of vector machines that make direct predictions about future events. In this autonomous architecture, it is possible to define computationally various forms of intrinsic motivations. These predictors noted are typically used to predict some properties or sensory motor states that will happen in the future, given the current sensor-motor context SMM times t, and possibly the past sensory-motor context. I have described and defined several cognitive robotic models presenting certain interpretation of intrinsic motivation in terms of properties of the flow of sensory motors, values of its relations to the knowledge of the system independently of the meaning of sensory channels that are involved in this engineering prototype. The engineering robotic platform integrates sensor fusion algorithms with sophisticated state representations. In the context of sensor fusion, a state refers to aspects of reality to be estimated. The state consists of quantities needed as output for the robotic prototype, such as guidance and orientation. Additional quantities are needed in the algorithms in order to model the behavior of the robot by mathematical equations as shown in this video. Autonomous vehicle systems. Preparing for the next frontier when thought, control, and thinking machines seamlessly brain-computer interfaces using fusion sensors to control autonomous vehicles as it relates to neuromorphic artificial intelligence platforms. The sensor fusion subsystem state model is based on abstract mathematical concepts, including position and orientation, in three-dimensional space. The state consists of three components: position, orientation, and velocity. Geometric intuitive correction algorithms and the support of quaternion Kalman mathematical filters form part of the artificial intelligence autonomous reference platform. Artificial intelligence methodology applied in this autonomous vehicle prototype. Machine learning, a subset of artificial intelligence, trains the autonomous vehicle how to learn. Machine learning mathematical models look for pattern in data. It needs granular data. The scope of this framework is to present and to illustrate a realistic artificial intelligence autonomous vehicle engineering prototype. Technology is influencing the way we do things, and metaphysics of artificial intelligence is evolving, projecting a new paradigm in developing new artificial intelligence, autonomous vehicles, and robotic controller systems. Pattern matching, image recognition, and object tracking form part of the artificial intelligence video system illustrated in this project. The objective is to illustrate a demo using machine vision technology in combination with a camera and artificial intelligence software algorithms to achieve image recognition. Image recognition, as it relates to machine vision, is the ability of software algorithms to identify objects, places, people, writing, and actions in images. Convolutional neural network takes advantage of the fact that in any given image, proximity is strongly correlated with similarity. That is, two pixels that are near one another in a given image are more likely to be related than two pixels that are further apart. In a typical neural network, every pixel gets connected to every single neuron. In this case, the added computational load actually makes the network less rather than more accurate. Image recognition convolutional neural network algorithms can function by use of comparative 3D models, appearances from different angles, using edge detection. Image recognition algorithms are often trained on millions of pre-labeled pictures with guided system learning. Pooling layer, which takes several dimensional arrays and applies a downsampling function alongside the special dimensions. The result is a pooling array containing only those parts of the image that are more important while discarding the rest, which both minimizes the computations that are needed to do while also avoiding the problem of overfitting. The neuron transfer. Once a neuron is activated, the need to transfer the activation to see what the neuron output actually is. Different transfer functions can be used. It is traditionally to use the sigmoid activation function, but you can also use hyperbolic tangent function to transfer outputs. The sigmoid activation function looks like an S shape. It's also called the logistic function. It can take any input value and produce a number between 0 and 1 on the S curve. It is also a function in which you can easily calculate the derivative, which is here. I show an actual design and implementation of an autonomous driverless vehicle. The autonomous system explicitly maps static obstacles, detects and tracks moving obstacles. The cognitive intelligent vehicle integrates GNSS technology, telemetry, gyroscopes, inertial guidance, and LiDAR technology, LiDAR. It also provides 360-degree high-resolution mapping with short to long-range measurement distance. It is also integrated by an optical front end, including signal conditioning, object identification, object classification, and algorithm-based decision-making software, and control synchronization with external light source. The light detection and ranging system is an active form of remote sensing, measuring distance to target surfaces using narrow beam of near-infrared light.